You're up.
For what?
To introduce our
Introduce
speaker?
Joe?
Yes.
I didn't know I was going to. I thought you said you were.
No, that's,
A double introduction.
Let's see what I remember. Joe, Kelley, and I have been friends for a very long time. We've been in school about the same time. He went to Lehigh, went to South Carolina. We crossed paths a number of times and go to the same place for job interviews, and I often came in second and Joe would be first. So if I recall correctly, he's from Maine, went to Lehigh University to do his PhD. Then he went to the University of New Orleans, spent a few years working there. Wanted to come back to Maine, went to joined the Maine Geologic Survey for about 10 or 15 years. Then a colleague of his named Dan Belknap was at the University of South Florida, also a Maine boy, came to Maine at Orono, and they've been working together for the last 20 or 30 years on the Maine shelf, the coastline, the beaches, the estuaries, and so on, and have had a very prolific and successful program at the University of Maine, in which Joe left the survey some time ago and joined them at Maine. And so he's going to talk to us about some of that work today. And the other thing is that one of our other colleagues, Duncan Fitzgerald, was at Boston University, and we were all in graduate school at different places at the same time, and friends referred to Dan and Joe as the boys from Maine, who've had this program that's been very successful. So, how was that, really?
That's all true. And when he left out all the bad parts. That's all good. I'm not arguing. Well, it's really nice to be here. Thank you for inviting me. I should say, for many years, I was the state's marine geologist in Maine. I am a geologist, so I know I'm not talking to all pure geologists like myself, but I use offshore tools and things as a tool. I mean, but for me, it's the problem I'm trying to solve. But for many years, the problem I had solved and worked for the state, about one day out of every 5 for 15 years, I put on my suit and I went to court as an expert witness for the state. That was a lot of my time, coastal zone management. And then we worked on a lot of projects, particularly down here in Wells and Saco and on beaches, beach erosion, so on the coastal side, on the land side of the ocean. But early on, I was tasked with making a map of the seafloor, and I certainly didn't have this DEM to look at. It really wasn't much of anything. And so when giving this, I haven't actually worked offshore in Maine for a couple of years now. I've been working in the Irish Sea almost exclusively. I thought about projects, but I thought, well, you're not really a geologist per se. So I thought I would go through a big picture of our intercontinental shelf, going out to about 100 meters, and just go through projects, problems that we've worked on. No one of which is long enough to put you to sleep, but I'll jump from one to the other, because often they end, for the most part, with, I'm not really sure really what the answer is. Because we go in, you study something, and then, well, it's sometimes ambiguous. And I know that two of my favorite graduate students, each of whom got masters and PhDs with us at Maine, have spoken here in the last few years, Laura Brothers and Craig and Walter Barnhart. I didn't want to bring in a lot of their stuff, just because I figured they talked about it, but maybe you didn't see them, I don't remember. So I will cover some of their stuff. So if you have any questions, just stop me, and I'll be happy to respond. So the offshore area here, we'll be going out not much more than here. I'll talk a little bit about this area, mostly in here. When you get up to this part of the coast of Maine, I don't know if anybody's ever turned on any offshore equipment. We never get funded to go there. You know, we get federal funds and it starts here and it ends someplace in here, and nobody cares about the rest of the state.
It starts again in Canada.
It does. Well, John Hughes Clark, to be fair, said they ran out of things to map. John came down and mapped all of it in this area for free, and he gave us the data. We got some papers. Okay, so where do I aim to?
You should just do that pointing here.
It's not working.
Nope.
Am I doing something wrong?
No, it may not be working.
Try the space bar.
That actually hasn't worked in a while. You have to
Where's
push
Put the cursor, maybe put the cursor.
push the down arrow.
Well, there's two sideways
sorry,
arrows.
the keyboard.
Oh, the keyboard. Oh, okay.
By the right
Oh,
arrow.
I see what it is.
I'll get you one that'll work.
Or you can do that.
Okay, so which was it, down or to the right?
Down.
Down, okay. Oh, you think it'll work now? All right. Okay, so the coast of Maine, really long, 3,478 miles, and the offshore is even longer. I mean, it's a huge area. And the state geologist, when I was first hired, said, come on in, make a map of it. Make a map of it. How about make a map of one bay? You guys don't want me to do that? Okay. So let me just go through very briefly the geology. I mean, bedrock frames the entire coast, and mostly when you look at a satellite image of our area, you're seeing bedrock. There's nothing else visible. When you get down a little closer, you'll start to see the second important factor. Well, bedrock controls the overall geometry, the shoreline and the offshore. The glaciation and glacial deposits give us all the material the ocean has to work on to generate coastal environments and offshore habitats. So the glaciers brought material in, deposited it, also eroded a great deal of material, and it gives us most of the character of our landscape that we perceive. I'll mention this a little bit later. As the ice left Maine, this was more or less the margin of it. It was on its way to the northwest toward Hudson Bay. Notice that the margin is subparallel to the coast of Maine. And that's important because often deposits are left at the terminus of the ice, and there are a series of glacial deposits that come right along the coast here. And if you look at all these lakes in Maine, most of those lakes are held back by glacial deposits. So when you look at the offshore area, you look at all of our embayments, realize that they were probably all lakes. In fact, almost certainly were all lakes. Great Bay was almost certainly a lake in the past. So these are the major features that are offshore. They'll be underwater and they'll be somewhat more eroded, but glacial moraines. They're big piles. This was the ice marginal position. The ice sat over here, and they come across most of our estuaries and embayments. I just gave a talk to the Friends of Taunton Bay the other day, and just showed this. Actually reminded me of Great Bay. Looking at this, you notice here's a glacial moraine right over here. Here it is sticking out. This was actually a lake probably only a few hundred years ago, and it's just transitioning into becoming a marine environment, though it is fully marine inside in terms of its salinity today. The major sedimentary deposit the glaciers brought us, aside from glacial moraines and till, is glacial marine mud deposited from ice tunnels like this one in Glacier Bay. Huge quantities of mud spewing out, literally drowning the landscape, draping over bedrock outcrops, covering everything for a fairly short time, but an outcrop like this probably formed in 50 years or less, very, very quickly. But the greatest volume of all the sediment in the Gulf of Maine is glacial marine mud. Sea level change. This is just to finish the backdrop. All right, so we have a glacier, we have a rock frame coast. It's been glaciated. The glaciers have taken some things away, brought in some new materials, but the glaciers weighed a great deal, and for about every 3 feet of ice, the Earth's crust was depressed 1 foot. So we had over a mile of ice along Maine and New Hampshire's coast. So the crust was significantly depressed. Even as the ice melted then, the ocean followed it inland, and we have an immediate higher than present sea level stand at about 50, 60, 70 meters. It changes as you go inland. But along the coast, this is in Acadian National Park, there's wonderful features like this sea stack, perfect analog to this one that's less than a mile away, a boulder beach, a sea cliff. So we had a higher than present sea level when the ice immediately left, but once the ice had gone away, the land rebounded and sea level would fall, and I would then come into the picture to study that.
Can you just explain that sea stack?
Sure. This is very much like this. This is part of the bedrock. There was a notch carved in it. There was probably an arch. The arch collapsed, and now it's freestanding. It is bedrock. It's fractured, but ultimately it's connected to rock. Very common erosional form, not on our coastline, which is the rocks are hardly eroding, which is remarkable to see that, but very common on coastlines where there are sedimentary, really soft, easy to erode rocks. So this one is much higher. It's up on Day Mountain in Acadian National Park, and it was recognized by a man named Shaler back in the 1870s as clear evidence that sea level was once higher. There are sea caves along here. There are all manner of things of that sort. He actually, I just looked at this and laughed. At Top Rock, he gave talks on this, and I read one article in a newspaper. He kind of embellished his talks and said, well, the last storm came as the glaciers were leaving, and it twisted that one around, and then the ocean fell down and went away. Well, it didn't look like that then. It actually came out as a point, but some of the good old boys in Bar Harbor, Maine heard that and came up that night with crowbars and knocked it off the top. And John Rockefeller owned much of this land, all of this land, and so he had a road built in and a crane brought up and had the rock put back, even though it was broken. And now it's been given to the National Park Service. There's no mention, there's no trails in here, there's no mention, it can't be talked about because we don't want any problems. So a map, this amber-colored area was where the ocean was. Probably not at the same time. Geologists would say time transgressive. It entered this area sooner than here, than here, than here. But you can see we were had a very different coastline. It obviously came down the Gulf of St. Lawrence and entered what is now Lake Champlain. It was up on an arm of the ocean. This is just a detailed map of the University of Maine area up in here in Orono that a student worked on many years ago, showing how profoundly different the landscape was, and it's still changing, of course. Some of the things we look at to measure sea level above present are deltas, and this is a beautiful delta. It's a blueberry barren today, but you can see the outer part of the delta. This is a cross-section cut into a delta. Here were the river channel things, and the river would get to the end into the ocean and drop down these steep, what are called foreset slopes. This particular one grew out quite some distance, but this contact between this angled bed and this more subhorizontal bed is a sea level indicator. So when offshore I'm looking at a seismic reflection profile, that's often the kind of thing you would look for. All right, the very first geological map I know of really in the Gulf of Maine was by Douglas Johnson. He actually wrote a good part of his work on his way over to World War I, published it in a book in 1925, but he hired graduate students to go out and do lead soundings with fishing boats, and he had many crossings, and he came up with this completely incorrect but hypothetical map that the Gulf of Maine was carved by rivers. Yeah, it was imperfect, obviously. He didn't know these are really closed basins out here. There's no way for the water to get out, and he didn't really like glacial ice ages and didn't think of those as much of an agent. When I entered Maine, this was the state of the art. I came in 1982. The U.S. Geological Survey had come up here on a cruise. They had some bottom samples, and I used to ridicule this, saying, well, every bottom sample becomes its own map unit because it sits so heterogeneous out there. But what they actually had done is they ran a seismic reflection profile, and they connected these dots with that, and were able to, in some ways at least, kind of draw boundaries. And I was thinking that probably was useful. It was later updated, simply digitized, and turned into a digital map by Larry Poppy and others at the U.S. Geological Survey. So there really wasn't much. And even this level of bathymetry, which is probably a 2-meter contour interval, stops when you get to about Portland. So there was nothing. So I worked in this area. We broke the coast up into 2 general regions. But really today, and for most of my life, I focused on this interval from about 0 to 60 meters, shallower inshore, but a lot more dynamic. As it turns out, 60 meters is about as low as sea level went in the Gulf of Maine. So sea level higher than present 15,000 years ago, fell to about 60 meters, and then has come up unevenly to the present shoreline. I just go through some of the samples. This is a lot of samples, thousands of drops, at least 1,700 samples. Focused initially, this was funding through the U.S. Minerals Management Service, BOEM today. That was the only tool we had, except each one of these had to represent a fairly large area. And one sample, just one, we actually got a Coke bottle, and I have a map somewhere showing the Coke bottle unit, since we had all the basis. But we did a lot of things, grain size and carbon and a number of other analyses on the samples. Actually, that's a great database if it's out there. The very first time I saw a side scan sonar, this was the run we were on. We'd actually, 1985, I guess I put 1986, it was 1985, it was an EG&G. And it was astounding. I realized bottom sampling was not going to do it, and just the variety. We just turned it off coming out of the Saco River, and it was bewildering and humiliating. Well, I mean, it did. I gave a talk based on some of those bottom samples. So we've gone through several generations. I say we, my close colleague Dan Belknap and I, have written a number of major research initiatives to the National Science Foundation, and twice gone through getting more digital equipment. I'm so envious of you all here. When I come around, look at the stuff you've got. Not only did we have to get this individually, grant by grant, if this breaks, I have to fix it, or my colleague Dan Belknap has to fix it. There is no technical support whatever. You go on a cruise to Glacial Bay, Alaska, and literally sever that cable, and that's hours to, well, I'm whining, but understand, we don't have a lot of engineers. We don't have any engineers that work with us. So seismic reflection was the first tool we went for. Side scan sonar was next, and we've used these things, as I say, through several generations of instrumentation. The National Undersea Research Program used to come into the Gulf of Maine. We got a lot of good ground truth from them. We bought several ROVs over the years. The vibracore is one of the nicest things. This is a 6-meter pipe, primarily because the U-frame on the back of the boat will only let us pick up 6 meters. It could go deeper, but we don't have a boat that's capable of getting it onto the boat. But it's an underwater electric vibracore, a couple hundred meters of cable, so we can go fairly deep, and it's been the key geologically to looking at what we remotely sense with geophysics to see what's actually there. Most recent acquisition, just sitting on it this summer, was the first time going out with it, was a multibeam system, which has been fun to play with, really nice and easy to use. But right now it's assigned to that boat, which is a catamaran we use primarily on lakes, occasionally in shallow bays.
Joe, is that the same wasp that the state of Maine is running?
Yes, it is. In fact, they were going after it. We both went in together and got it.
It's the same system?
Same, identical system. The nice thing is we didn't require a technician with it. You would walk off the boat and it's there, but it's not nearly as accurate as some. So, just a general thing. We're actually going to write a paper, several of my former students and I this summer, we promised, about the seafloor out here, but I'll go through these various units. A near shore ramp, a gentle seaward sloping sand and gravel area, rocky zones, just what it sounds like, vast areas of either bedrock or really hard bottom, gravelly. Outer basins I won't talk about all today, but much deeper water, generally muddy. Shelf valleys, to me, are enigmatic. These valleys cut through canyon systems, really cut through the bedrock. As you get inland, they become filled. They're completely filled, but in the offshore areas, they're generally just deep rock channels. Way too many of them to have been carved by a river, and often with the wrong orientation, to have been carved by glaciers. I'll just say this in advance, I believe they were carved by large volumes of water that reside beneath the glacier lakes that were released catastrophically. Very often they follow what appears to be the outline of rock contacts, different kinds of rocks. So I'll talk about, first of all, I will talk about the rocky zone. I don't do much work here, and I won't say much about it. It's rocky. I'm a geologist. I'm looking for a record, some kind of a geological record. Just some of the bottom samples, most of them, 71%, don't even plot because nothing came up after 3 drops, but those that did were essentially gravel and sand for the most part. Again, we don't do much work here. Seismic line, we get no penetration to speak of. Some small gravelly areas. This line is a side scan image here. Just very rocky. I never thought, I mean, we just would turn off equipment when we thought we were going to be over these areas for a while. Biggest project we were involved in was the offshore wind. Maine is looking to put wind material out, and they initially wanted to work over mud bottoms, but they came to realize there was a lot of rock out there. So it depends kind of anchoring system you want. If you're in mud, you can use something called a suction casing that really needs to go down deep in mud. But a lot of the areas look like this, and you're not going to do that, so they move toward gravity anchors. But there's one area we did work in a hard bottom. It's not that far from here. Wells is just up the coast. This is the original multi-beam record that was done in cooperation with my former student Walter Barnhart from the USGS and its hardness, and became interested in this upper area that I've encircled there because it had a number of curious things. This is just a seismic reflection profile coming up on that area. What you can see is the bedrock is down below here, and here's a glacial till deposit with a lot of topography. These would be small moraines, minor moraines, and occasionally they poke up a little bit above the bottom. but mostly they're hidden. But in some areas, there were just a whole series of them, all parallel to one another. And the beauty of these, when I looked at them, was that you know, they're ridges, they're large ridges, maybe 7 or 8 meters high or higher. They were deposited underwater in about 80, 90 meters of water when the glaciers were retreating. So they were deposited underwater. They emerged as the land came back up. So each of those rose through the surf zone, were reworked by waves. Beaches probably formed on them, and in a sense they were barrier islands. And I used actually with this particular image, I was planning a coring expedition thinking, this would be great areas, because then sea level rose again and eventually would drown them, but here would have been a beautiful tidal inlet, and many of the things we look for to core to understand sea level change.
Joe?
Sure.
Can you just tell us in these images whether high backscatter is dark or not?
Dark is a hard bottom, it'll be gravel. That's all hard. In fact, that's what is intimidating about this, is it's really hard. It'd be very hard to core into boulders. I found this on the internet. This is what's happening in, I think it's in Sweden today, where similar systems, identical really, are emerging here. So that's what Maine's would have looked like. There are a number of them off Marblehead area of Massachusetts too. Well, I went through this just in a very simple model in my mind and thought, okay, why are they still there? Why didn't they erode? The ocean had 2 opportunities to erode them. If you go along the coast today, these features are being cleaned off. And I said, well, you know, they're maybe the average 10 meters. And I went through the rate of sea level rise. Well, you know, over the time, it's just, you know, erosion rate of 1 meter a year, which is pretty rapid. They'd be gone in 300 years, but sea level rose far more rapidly than that. You know, a more reasonable erosion rate, they still would have been to some degree out there. But I couldn't fathom why they were so well preserved. And so we used a model, a wave model called SWAN, and we basically lowered sea level to approximately the depth so that these were coastal features at the time, and we're able to bring in the kinds of waves that are typical now and presumably in the past in those areas, and model where the wave energy would be strongest and where we would then begin to look for environments we could core. Unfortunately, that was the year the money ran out. There was no more money. We've never gone back. All of the data is there, all the records, all the target sites to core, but so if you ever have a student who wants to core, I'm going to vibracore. If you've got a boat, there's some great targets out there to work on. One of the most conspicuous areas here, you spend a lot of money are off beaches. These yellow areas, these nearshore ramps, sandy, always extending from a beach in an offshore direction. This particular one is, we've called it the Paleo Delta of the Kennebec River, largest river in Maine, comes in right here. And this was approximately the low stand of sea level out here. So this delta formed at the time sea level went to its lowest location. An ideal place then to look for sea level change, and it became Walter Barnhart's PhD thesis. The samples from these areas are invariably all sand or maybe some sand and gravel mixed together. And this was the map was made from a side scan sonar, long series of mosaics over the area. It's still very patchy. We became interested in the alternation between the green is gravel and this yellow, which is more sand, and what was actually going on. Another person, Steve Dixon, who's the state marine geologist now with the Maine Geological Survey, took that as his dissertation topic to put current meters out here to figure out what was going on here. I'm sure you have features like this off the New Hampshire coast on an acoustic image. That the gravel areas are all rippled. The sand is rather featureless looking. Long story short, though, what it turns out is that there just isn't enough sand. The sand is the bed form. This is actually moving. And these move over time and begin to migrate across these areas. If there was more sand, we wouldn't see through to this, but the gravel retains those ripples really nice. But for Walter's work, we were interested in sea level, and again, here is the old delta, here are the top set beds, here are the four set beds. This contact then right there at about 60 meters represents the lowest sea level got in the central Gulf of Maine. It was lower still here. It's about 50 meters off a similar feature, the Merrimack Paleo Delta off the Merrimack River, and gets somewhat deeper, I think, as you move toward toward the Bay of Fundy. This then mapped a series of shorelines, some of them which were active as sea level rose and came inland, which we targeted to core. The only one I mentioned, I show this one here. It doesn't look like much. It cost a great deal of money. There's some barnacle shells, a couple pieces of wood. These were the only datable or things that we could find in a whole series of cores from out here, one after the other after the other. But they were datable, and they became the basis for our sea level curve. So in my area, and to a degree around here, you know, again, sea level was very high at the end of the Ice Age, about 16,000 years ago. Because the land was pushed down, sea level fell, the land actually rose. Sea level was rising this whole time because glaciers were melting. Sea level fell to a relative low stand. These were Walter Barnhart's contributions to understanding that, getting some dates that seemed to give us a time. Then sea level rose rapidly, slowed for a long period of time, rose rapidly, and then has continued to rise, though very, very slowly toward the present. So we developed, from working in these nearshore ramps, a really good understanding of sea level. I'll talk in a minute about where all of these dates come from. One other nearshore ramp, Old Orchard Beach, a major, the largest beach in Maine. Huge controversies down here at the mouth of the Saco River. There are some jetties. One of them is 6,668 feet long. And it was built because a little anchorage in here, the Corps of Engineers couldn't maintain it. They alleged that there was a glacial deposit out here under the bay that was eroding, producing material, and that material, sand, moved down here and was blocking the harbor. So they began these jetties. And they never entertained the thought that the river might actively make a contribution, which, long story short, it is the source. We mapped the entire bay with side scan sonar and seismic deflection. There's no glacial deposit at all. When we came over here and we mapped this, the bed forms on the bottom are all oriented downstream during the spring flood. It's a major contributor. All of our major rivers in New England contribute sand actively to the continental shelf during the springtime. So we took this, and for a student's thesis, we turned it into a sediment budget. We went out and used our offshore records where we could see here's the glacial marine mud, which is at the bottom, but here's the seafloor, and there's this wedge of sand that actually becomes what you see here, colored in terms of its relative thickness from less than 1 to as much as 7 meters. So we use seismic reflection and coring to establish the thickness offshore. We use ground penetrating radar and augering to establish the sand. So we knew there's 56 million cubic meters of sand in this system. We estimated the rate from some current meter estimates that we had, which was crude, but it kind of paralleled what the Army was dredging, about 10,000 cubic meters a year, and we tried to work out a sand budget. It's turned, like so many things in science, it's vastly more complicated than that. We deployed seabed drifters. They end up all over the place. They leave the bay and you can go, it's much more complicated than that. But it's interesting because the Army is going to come back this year. They've come to acknowledge that, in fact, sand is coming down the river. They're going to build some breakwaters here. Tremendous erosion has occurred adjacent to this, and they're going to try to protect it, and there'll be an abundance of money made available to monitor changes here. And I'm hoping monitoring changes in the seafloor will be one of the things they're interested in. Continuing that, I mean, the outer area here, there are some rocky areas in red here and some gravel, but I was interested in sea level low stand and thinking I'd find a delta here. There is no delta here. There's a river, but actually the river way upstream enters a lake and deposits much of its sand load. Still some sand gets down, quite a bit, enough to build this system in about 7,000 years, but apparently not enough to have built a big delta. Though there is sand, and this is the way it is. It's around the outer side of the bedrock ridges. So, thought to study sea level change, we'd go out and collect cores, and we did a lot. I won't even show you how many. I was certain this was just, I was going to core down here, go through a little mud, and then go to some kind of a beach deposit. Never, not one time. Young dates, too young. Interglacial marine mud on the bottom, too old. Nothing recorded. One very fortunate core back here, goes through glacial marine mud, this blue. This is all sand that flows in from the side of the core, is not actually in place. This would be massive mud deposit. We've got a beautiful Maya arenaria in light position, 2 shells articulated right up here, which was really was one of our best sea level indicators for a long time. But I was really disappointed. We couldn't find anything there. And later, this was with BOEM money, they came around and wanted us to find sand deposits that they could use to replenish, particularly this eroding beach here. And I focused on this area, thinking, okay, all right, there's no delta, but there's sand there. What is its structure? What is it doing out there? And it's a long story. It was Kristen Lee's master's thesis, and I said we wouldn't publish it until she wrote it up, 2007. She's finishing her PhD, I think, this year at the University of Washington. And if she doesn't get to it, I will write it up, because it was really great work. But we basically made a multi-beam bathymetric map over that area I just showed you, and we were interested in the approximate depth of the low stand, shown as this white band, and there were big, wide platforms. In areas where glacial deposits and bedrock erodes, they're often wave-cut platforms, and that's what these looked like. But in a number of areas, it was interesting because it appeared that there might have been coves and lagoons. So again, we used the GIS to lower sea level, and look at this, use 60 meters and 50 meters below present, and then to use a wave refraction program to see where wave energy was. And it was interesting, it was where sea level had dropped, when sea level had dropped, Saco River had come over here. There were eroding bluffs probably nearby of glacial material. But there were a number of sheltered areas back here where we found potentially lakes. There were embayments that would have been deep, but they weren't connected to the ocean. And then as you let sea level rise a little bit, some of these lagoons become mud flats. So that became our model for our coring target, which we did the following summer. This would just be one of the lines. We cored a lot out here. This is a side scan sonar line that's probably about 200 meters across. And we were looking for targets that in the seismic reflection records looked like they would be an unconformity, modern sand resting with an erosional surface on ice age mud. So we had a whole series of them, and I didn't know where they would fall out on that until we plotted them. And curiously, they're all near rock, but these turned out to be all great targets. This is just one of the lines. Core here, here's bedrock. I guess it's interpreted down below. There's glacial till deposit above it, glacial marine mud, again, always the dominant, and sand above. So clearly an erosional feature in between, an unconformity. We cored down on it. The bottom of the core was all glacial marine mud. And we come up and bang, it hits you very suddenly. You change right into the sand. And right at that contact, right there was a clam, Maya arenaria, still in its life position, vertical, 2 shells articulated, absolutely died there, probably smothered when some sand came over it and covered it, and it dated to 13,000 years ago, which was very exciting, and I can't wait to see this written up. So, really good records when we could finally start to bring more technology to bear, particularly positioning technology and imaging the bottom, so we weren't coring into unpleasant things like gravel. Continuing up this way, I'll talk about nearshore basins. Probably done as much work here as any place. These are relatively flat bottom mud, thick mud deposits, generally in our estuaries. Not so many here, but they continue on up the coast. You could just call them estuarine deposits. Many of the shelf valleys here, etched in bedrock, come up into these areas. These were old river valleys, and they are filled with mud once you get into the nearshore basins. So they are, as one might expect, muddy. 77% of the samples were mud, 100% mud. This is where I had a great idea once. I was standing here, and we were working on sediment accumulation right out here. We had a number of sediment traps. Where's Kelley? One of those is Craig's ship. That's Craig in the yellow there. I was looking at this, and a homeowner had just come over and talked to me and said that, this is about 15 meters high. He said, yeah, boy, they drilled a water well. It went down, I don't know, another 60 meters or so. But, wow, there's a thick deposit. This was once a big river channel for the Androscoggin River. And here it is being eroded, mean high waters right down here at the base. Here go these trees falling in. There's a little bit of a salt marsh growing here. There's clams out here. These are all datable objects that would be really great if they were preserved on this surface. If you dig down just a few inches here, you're in the same Ice Age mud deposit. And yet modern mud, which is just this stuff after it's eroded and goes out into deeper water, will cover it. So another unconformity will form as this erodes back. But that unconformity has the potential of protecting trees, salt marshes, and clams. So I thought, well, why don't we run some seismic lines offshore here? And there were lots of them, but this was one. And what you see here, here's the seafloor, and it's coming down. It's acoustically transparent here for the most part. Here's the Ice Age mud deposit. Here's some bedrock. Here's bedrock, and wherever there was a rocky ridge, the mud just drapes up and around. So it looks like it's folded. It's not. It's just the original way it was draped. Actually, this was with our original 3.5 kilohertz device. And so I said, all right, we'll core right over here. I know we can get through it. And beautiful shells all right on this horizon, really radiocarbon datable. This has proven to be the way to study sea level change, is to follow this erosional surface, which is, again, the base of that eroding bluff. It's an unconformity, to follow it out until it goes to conformity. And it was work that I did in Ireland on a sabbatical where we did just that, and we were astounded by it. And in Ireland, they have I had an idea for many years that there was a land bridge and people walked to Ireland, all because they found a freshwater amphibian there that was thought to have been there a long time, and they don't go in the ocean apparently. But, well, long story short, having seen this, we just spent the last few years on cruises in the Irish Sea, following these unconformities, sometimes finding deltas, sometimes finding beaches, but always following these and collecting hundreds of cores, which has established, in fact, one paper is in review, the others are coming around, but despite the National Geographic's beautiful map 2 years ago showing rivers in the Irish Sea, it's all bogus. There was never there. They voted to Ireland. There was never any possibility that there was a land bridge across there. So I told
have a question about the mud.
Yep.
Is there any way to leach out the organics that might have been in the mud at the time that was deposited? Just things like pollen and all the rest of that.
Yes, I've never done that, but
Yeah.
it is certainly part of that record,
Yeah.
without any question. Yeah. None of us have ever done that. In Ireland, we did look at foraminifera that do live in tidal flats, and could separate out enough of them to get radiocarbon dates. They're sand size. But no, I've not ever done. We have so many cores, and we were looking for a shell. Find the shell, date the
Solid
shell,
carbonate.
log the core, and then off to the dump.
Yeah.
One sample off there, the same general area, marvelous, probably unique. I've never seen anything like this really. Here's the top of the core coming down and coming down. This was taken right on the deck. But we cut it, and beautiful right here. It's glacial marine mud down below here. Goes up into what was a tidal flat, a salt marsh peak, probably the deepest preserved salt marsh peak. This is about 24 meters below modern high tide. And then mussels and undoubtedly clams before he went up into deeper and deeper water. So a beautiful preservation of the record. Also from a student who didn't publish papers, so that's never been written up. But great work out in there. Finally, I'll mention some other areas that are really estuarine. I'll talk about up in here. This is looking at the paleodeltas on the Gulf of Maine. The Merrimack is the largest. Written up by Walter Barnhart and more recently by Chris Hine and others out of BU. The Kennebec I've talked about, another large river. The St. John does not have a paleodelta. It enters a major lake before it comes to the ocean, dumps its sediment, at least its sand, and so there is nothing offshore. The Saco has rudiments of one that I've showed, but it's a smaller river. But what about the Penobscot? We could find nothing there. We couldn't understand why. Something profoundly wrong. Okay. Just a backdrop to the story. This is my wife's story, actually as part of her dissertation. Here's the drainage of the Kennebec River in green, of the Penobscot in blue. Here's Moosehead Lake, the largest lake in Maine, and you can see it is very close to the divide. In fact, the divide today is right through here. One of the best students I think we ever had years ago, I was talking with him, he was trying to come up with a project, and I said, just as the ice loads the ground, as it moves to the northwest, it pushes down the area to the northwest, is pushed down more than the areas here. They're already emerging by the time the ice moves back. So I said, I bet these lakes tilted, and we knew, I said that knowing that there were lake deposits known that are above lake level out in this area today. In fact, I found all the big lakes are like that. The slope of the land surface at the time the ice was moving was about 0.4 meters sloping downward toward the northwest, 0.4 meters per kilometer. That's a steep slope. I mean, enough so, I think I've got a picture of it. No, I didn't put it in, but enough so that this area, which was where the ice had left last, was well pushed down and allowed the Moosehead Lake to drain through this channel that you can see right here and connect to the Penobscot drainage. So the two biggest rivers in Maine had exchanged a big drainage. The important thing about this is, one, there's a lot of water, and two, it's high mountainous area that experiences a big spring meltdown. So thinking about that, we wondered about it, and my wife Alice here went out and did a ground penetrating radar profile out across these areas, and you can see the outline of the channel, and in the bottom of the channel there would be peat today, but below that, when it was a river, it would be inorganic, and was able to come up with dates around 8,800, 8,900 years before present, which was just unbelievable to us because we had, when working in Penobscot Bay, this is Penobscot Bay, the Penobscot River and the University of Maine are up here. We've been through here a lot. The U.S. Geological Survey had two large projects here. It was Dan Belknap looking at some old data that finally noticed that there was a large sand deposit here in Penobscot Bay that we had never even seen before. And the reason we hadn't really noticed it is that it was buried by mud. Here's this thick modern mud deposit, 10 meters or more in some places, covering it. So what happened here was there was a delta of the Penobscot River, and it was sandy, but the drainage changed. The Kennebec River captured a significant amount of the drainage of the Penobscot and left it with not enough water, not enough discharge, not enough competence, we'd say, to transport sand. And so all the sand in its channels got locked in because the discharge never got strong enough again to move the stuff out. It's a river that's undergone some big changes, but by the time that happened, no more sand would come down. Only mud comes down the river today, and it buried everything. But this bay would have looked like, like the mouth of the Kennebec River, Popham Beach State Park, big sandy beaches, Saco Bay, Plum Island National Seashore. Would have had sand everywhere, but it's completely locked up by the mud that overlies it. I don't know, does anybody remember Stephen Clayson? See, I was going to show more of that, but Stephen was a student at the University of New Hampshire. He was a maritime archaeologist, and he called me one day, and he said he had an idea for a project that I want to work on. I don't know why he didn't ask someone here, maybe because I'm in Maine, but people have been coming up with archaeological artifacts out in this area, which I thought at the time was all just a bunch of mud. And he said, well, why don't we go and do a study and see what the context of these archaeological things were? It wasn't even a hypothesis. It was like, let's go fishing, and that'll never get funded. I didn't even want to waste time reading it, but he persisted in telling me, we got to do this. He's very persistent, and I'm glad he was, because he was really right. It was incredible work that we got to do. Every step of the way, I had to be prodded to do the next thing, but we went out, and these were some of the artifacts that came from this particular site over here. Again, there was no hint of what was on the bottom from what was available on the nautical charts, but I don't even know whose multibeam it was. It wasn't mine. I didn't have one then. But we did a multibeam map, and we could see this is where the artifacts had been more or less coming from, according to a scallop dragger who had dragged them up. He knew there was a ridge there. What you're looking at is the remnants of a glacial deposit, of a moraine, and it would have been oriented more or less this way. The wind in this area is predominantly, as it is in the Gulf of Maine, out of the northwest, particularly in the winter. All kinds of islands here sheltering this from the open ocean. So you can see the erosional scarp along the top where waves had eroded the deposit and all the boulders exposed from the glacial deposit. And the eroded material, largely sand, formed spits and beaches through here. This was the seismic reflection profile through there. Unfortunately, the way the money came, we did this the second year. We did this the first year and decided we were a core before we even saw that. But I said, oh, this is great, because that looks like a sandy beach over glacial marine mud. Perfect feature to core, and core we did. This was that core, and it was at the top, well, let's start at the bottom. The bottom, it was very sandy shells, just unbelievable. An oyster reef, completely preserved, one oyster attached to the next. A lot of Maya, arenaria fragments, and a lot of whole pieces. So we had no shortage of dating. Most of the dates were in good stratigraphic order, with one anomalous fragment, which I would never have sent in, but Stefan sent it in, and we got it dated, so we reported it. But so that goes up through here, and then it changed into a muddy area. Part of that beach grew out and protected it from the ocean. This just shows some of the shells. And we go up into the upper part of the core. We went into a long, thick mud deposit with big plant fragments visible and pebbles here and there. That then transitions abruptly into sand and gravel. This represents the drowning of this environment as sea level comes over it. So we got a lot of radiocarbon dates. These are beautiful cores, as good as anything I've ever collected. This is some of the plant material we saw all through this area here. We even dated one. We peeled it off little by little. It's still green. Zostra marina, eelgrass. So there would have been an eelgrass bed, just like you'd find today. Perfect environment. Really some of the best radiocarbon dates to study sea level change that I have ever collected, or anybody may have collected offshore. So we ended up with a series of papers in prominent journals. Here was the bay. Here are the shorelines, and there are many of them as sea level went down. You can see the breaks in slope that occur all through here. There were eroding glacial deposits that fed sand into beach systems. There was an inlet, and there was a tidal inlet, and then there was an inlet stream. This would have been rapids coming down. And Native Americans would have had little trouble living in a place like this. It would have been a freshwater lake alternately, and a tidal flat later, and eventually, of course, it would all drown. So it became our model for understanding, why here? Why is this so well preserved? And these were the dates we got from that project. Really focused on this. It made me focus on it. Wow, what is it about this? So many dates here. There were so many things to date. Between, 25 and 15 meters depth, and that's certainly the case here in New Hampshire, was a time when sea level slowed down or nearly stopped its rise. Well, if you stop sea level rising, or even slow it down a lot, waves begin to work on one place over and over. They begin to really erode glacial deposits. But in eroding them, they produce sand, so they produce beaches. They produce habitats in which mud can accumulate behind the beaches, marshes, tidal flats. So these are all tidal flash and salt marsh dates at a time when sea level's not rising, because that's the time when you can form modern habitats out of the erosion of glacial material. Glacial erosion is, all sediment erosion is most complete during this interval. Then sea level rose rapidly, left this all drowned and really beautifully preserved. So it became a model for understanding. If you want to go out and look for archaeological deposits on the shelf, where are you going to look? Well, get a sea level curve first. When you see something like this, this is the interval. That's the depth interval that you're most likely to see the best preservation of any terrestrial sediment, meaning salt marshes and nearshore coastal sediments. And the time interval and the depth interval most likely to be associated with any remnant archaeology that you're likely to recover. Well, I wasn't going to talk about that. I threw this in at the last minute because I didn't know if my student Laura Brothers, I know, gave a talk here, and she talked about this. But you can disagree with your students. They can still get their degrees. She got a degree. She got 3 degrees with me, 2 masters and a PhD. And I don't agree with her. And so I know she wouldn't have shown my slides because she doesn't like them. But what you're seeing here is natural gas, shown in green. You know, natural gas is methane. It'll be contained in the modern sediment, only the last 10,000 or so years of sediment. And in some areas, there are really nice gas escape pockmark fields. Actually, more than that now. This figure's a few years old.
Your tracking of natural gas is based on what?
I'll show you. Oops, go on. Okay, this is how we developed it. These would have been seismic reflection track lines. And where lines go over an area that's mapped as gas, it looked like this. If there are 5% or more bubbles in the interstitial spaces of the sediment, the sound at the frequencies I'm using will not penetrate that. They'll reflect strongly. NG, natural gas. So there's too many gas bubbles here. I'm not going to get any penetration through that. Typically that meant just snooze until you get to something to look at. But here, clearly, it meant that there was a significant amount of natural gas. And in many instances, in this instance, and right here, the gas has probably migrated up along this pathway, escaping and excavating a small depression here. Not very, that's probably only about 3 or 4 meters. But in other places, they're much larger. So we recognize it on the basis of seismic reflection.
What is that cap? What's the HM?
Holocene mud. This is fairly acoustically transparent. And this would be the glacial marine. This is the unconformity, the erosional surface. This probably would have been a valley filled with salt marshes and things that could generate.
So is the gas in the glacial marine sediments, or is it in the mud?
That's a really good question, Larry, and that is a question we've debated. My colleague Dan Belknap and I are of one mind about it. Some students had other minds, but they've been persuaded. It is entirely in the Holocene. And I don't know if I have a record here to show you, but it is entirely in the Holocene. If you get into the glacial marine, there isn't any. If you go into the deeper Gulf of Maine, there's natural gas, and there's no, it's obviously much deeper water. There is modern mud, but it seems as though the gas is actually in the Ice Age material, but not any place I've observed in this area. So some areas, I don't know whether this is plankton or fish or what it is, but we thought we saw some suggestion of gas escaping, but became interested in all these areas because all of this is pockmarks, all of these, and these pockmarks are not small features. They are the largest undersea landform in muddy environments, period. This was a paper that came out from a student. We just went out and made a map of the area a number of years ago. You could put this building in this one here. These are gigantic, 350 meters in diameter, almost 40 meters deep. I don't mean deep water, I mean below the surface intrapockmark area. Really large features. There are more than 2,300 in this bay, and they're in every bay. John Hughes Clark came up and did Blue Hill Bay, Somme Sound. There's nothing but pockmarks. Local people know about them, lobstermen and so forth. Lobster goes out here. The slope on these averages about 30 degrees. So a lobster goes in there, he doesn't come out on his own. People would dive in. And the harbor master in the town of Belfast here, a very sober man, said he was out. I didn't even know you could legally harvest lobsters by scuba diving. Maybe you can't, but he told me he was. And he said they were down in the bottom of the wall, broke open, and bubbles started pouring out. They were sure they were going to be killed. They said it was like being in a Coke bottle. It was just bubbles coming out, and it lasted a few minutes, and then it stopped. And well, I've had about 4 or 5 graduate students do theses on these, and I think someone from the University of New Hampshire did a current meter study here, which is excellent because that needed to be done. Laura Brothers' work was to look at time series with the U.S. Geological Survey's multibeam and positioning systems. And the bottom line was we found no new pockmarks had formed over this interval, which is not that long. No old pockmarks were filled in or gone. In fact, there was no detectable change. They put a plus or minus on detectable change at about 5 horizontal meters, meaning there could be slightly different offset, but that was assumed to be based on just navigation errors. 5 meters seemed large to me, but I couldn't argue with the person telling me this because he was really much more expert at it than I. So essentially the field hadn't changed. It's not a long time, and again, the margin for the change is a fairly coarse one. It's well worth continuing. We do have fairly good records. The earliest ones were not the best. The later ones became better. They are everywhere. They're in every bay, going up the coast into Canada. You know, what's the origin? So I leave these as some questions. What's the origin of the gas? Is it terrestrial? Is it marine? Is it estuarine? Is it something else? It's definitely not something else in the sense of deep-seated natural gas. If it was deep-seated natural gas, it would have propane and butane and all those other alkanes in it. It does not. It's pure methane. So it's almost certainly derived from the bacterial breakdown of plant matter from land or sea or estuary. When did the fields form? When did this happen? They're the very first bathymetric soundings by the National Ocean Survey clearly shows them. And I can imagine that they're going out on a flat, muddy bottom. It's 32 meters, 64 meters, 32 meters, 32. You know, did you make a mistake there? How could that be? Well, they mapped it, and they mapped them fairly well, though crudely. So did they form all at once due to an earthquake? Did they form slowly, and are they a natural part of the evolution of our estuaries? And I don't know that because I haven't really figured out a way to establish when they began. They're found in glaciated areas, Long Island Sound, Narragansett Bay, all the way up, all through the Canadian Maritimes, Ireland, Scotland, the Baltic, but they're not in Chesapeake Bay. They're not in Delaware Bay. They're not in Houston, Galveston Bay. They're not in San Francisco. There are no other estuaries, only in, well, not only, but predominantly in glaciated estuaries, formerly glaciated estuaries. They exist over oil fields, certainly, and that's easy to understand. It's a very different kind of a gas there. They exist in tectonically active areas like Greece and areas where there's a lot of shaking. Hence, I go back to thinking perhaps an earthquake formed these. Are they active today? I don't accept that they're not active. I think they are. I've been out before with an oceanographic class, and we saw just plumes of mud in the water where there was apparently an active pockmark release. But those might have been small compared to the ones that formed them. Once formed, as has been shown by a student from here, as well as some modeling that Laura did, tidal currents will maintain them. They are non-depositional areas. They'll be scoured and maintained and even enlarged. But as to when they formed and how active they might be, those are all fundable NSF problems, I think. So where does it come from? I'll just offer you this is what Laura would never taught. She hated when I showed these slides. But you know, if you go to the Maine coast, I mean, it's a long coast. This is an area with a lot of peat bogs. This one right here is right here. You can see it's a freshwater bog. Its raise is about 3 meters higher there than over here. That's a salt marsh, and there's the ocean. Clearly, this is a dynamic environment, and one in which the ocean is going to win. It's going to consume this, but this bog probably goes down 10 meters. So there's going to be a lot of organic matter preserved at the bottom of it. That's just a close-up photo of it there. So there's one way to do that. Lakes are, of course, another way. And I showed Taunton Bay, which was clearly a lake once before, now is becoming an arm of the ocean. These are eroding all along the coast of Maine, and it's a way to get organic matter, lots of it, out into the ocean and get it buried by modern mud. So my cartoon, which we did publish in 2004, I think, shows how this formed. Here's the ice sheet. Here's an ocean at the time of sea level of glaciation ending, icebergs out here, a bay filled with glacial marine mud. Sea level falls to a low stand. We have some basins here. They become lakes. A lot of organic matter forms at the bottom, accumulates at the bottom, and then sea level rises, and time goes by, and maybe an earthquake happens, something happens, but we've got to trigger this. Once gas has a way to escape, once it's got a pathway, the gas will continue to follow that pathway. There are a lot of experiments done, but it will always go through the same pathway. So when you see veins, like white veins in rocks, those are pathways fluids use to escape. And once the fluid has a pathway, it doesn't look for new ones. So I tend to look back and say these are probably all primal. They formed originally. Some of them, the gas clearly migrates, and we can track the migration of the gas. It leaves bright spots on seismic reflection records off to the edges where the gas migrates out here. Laura, I should be fair, Laura thinks it's just coming out of the estuarine sediment. None of the pockmarks go down below into the glacial marine. They bottom out right on it, giving it a fairly hard-looking bottom because it's a much denser material. So this is just the next proposal, I suppose, that I'll eventually get around to, but looking at the large earthquakes in this area, how do we understand earthquakes in the past, deep past? One way is by what are called clastic dikes or sand blows. Area when the ground shakes, water is released from deposits and moves upward, often erupting on the land surface as a large body of sand and water that pours out. Well, then they can be studied, they can be dated. This was on the North Shore of Boston a number of years ago. Other areas people have seen evidence for gas triggering the earthquakes, rather triggering the release of gas. This is my favorite picture. It was newspaper report that wrote about our stuff. I just love the drone. I would never dare to publish that someday, but it's not. It's, you know, it looks dangerous for the body. I don't think it is, but that's in essence how it may have happened. And then a quote from the father of marine geology: you know, sea level were lower. You know, there have been lakes everywhere, but we've never really for sure seen a lake. All right, last segment, and is just to talk about these shelf valleys. I've done almost nothing in them. They're a mixture of sediment of many different sizes, mostly mud. These are probably really important pathways for getting material offshore that's escaping from our coastline. This is one in Casco Bay. Two tributaries appear to come together. We actually dove on that one to see what it was, and it was just a hard, shelly area. Many of them are also filled in, though. You can see the channel still remains, but not on the surface. This is the largest, really, really deep, right off. It's over 100 meters deep, right off Rockland, Maine. Major channel system. You can see how convoluted it is. It doesn't look like it's a modern river channel. Glaciers would have crossed it at an angle. I don't know really what it's doing. How did it get there? I think subglacial meltwater, huge quantities of water charged with sand under high pressure may likely have scoured it, but I don't know that.
You mean through bedrock?
Well, these are actually bedrock contact. That's a granite body, and that's a contact. No, the ice would have been up here, there would have been a lake behind it, and it would just discharge catastrophically. And it would have been charged with sand, and as it did, that pouring out of the water would have etched into the bedrock. That's just, I don't know that. And
Is there any relation to fracture patterns?
To which one? Fracture? Yes. When I say this is a granite, this is some kind of other kind of rock, so there's a contact here. That contact would be prone to fracturing. That's the area you're gonna, you know, every place got the same kind of stress, this is the area that will erode out first. Others I can't know, I've not really looked at the rocks, but I'll bet that they follow weaknesses in the rocks, contacts between units. So really neat areas. You want to put a tidal power thing in. Much of the water that comes in and out of Penobscot Bay is coming right through here. I mean, that's where you want to put your tidal power station. I just threw this in because I knew I was coming down here. They're every place in the Gulf of Maine, and they're every place in glaciated terrain. This is Jeffrey's Ledge, major system out here. This is a glacial moraine, and almost certainly used to cross here, but has been eroded out by something.
So before you leave that one,
Yeah.
the stream to the right, if that's what you're talking about, you think that's a subglacial stream that
Yeah,
eroded down?
I think so. I think so, and I think it might have come up from off here, but again, there's too many of them. There's so many, there are more of them than there seem to need to be. But, I mean, there is no other explanation. Glaciers, bad orientations, rivers, way too many. I don't have something else. Combinations, yeah, maybe. But I've seen images from Antarctica. There's a lot of features like this there. That's how they're interpreted there. So, to sum it up, sediment in the Gulf of Maine, I mean, most of it, we really didn't go into the deeper water much, but it's mostly muddy, and I don't have a lot of interest in that, really. Most of the underwater area that we've mapped has come out generally as rock. Mud, particularly if you're going to incorporate some of the deeper areas. But some of the best areas have been sand and gravel. My last slide, you know, how far away were we from the dock? A quarter of a mile. The captain of the boat had been there for 13 years. And how did we do it? Well, we wanted to go, people get obsessions. I want the seismic line to start right at the rock so I can see the rock fall beneath the record. And that was Craig Ship's, in fact, that's Craig Ship who took these. And one thing, this fellow was a grad student, he was older than I was, but he had an obsession with it. There was a big board floating out in the water. We had to stop and get it. We couldn't let it go by. And this happened, we were locked in as the tide was dropping, and we were going, oh, it's all our new equipment. What are we going to do? We're going to tip over probably. And he had all this lumber. And literally, you want a grad student like that who can go out with no warning and save your boat and your equipment. We'll owe him eternally for that. So, thank you. I think that's the last. Yeah.
I'd make an anecdotal comment
Sure.
about Passamaquoddy Bay, which also
Lots of pockmarks, yeah.
tons of pockmarks. And again, this is only anecdotal, but supposedly fishermen have seen bubbles.
Oh, they have. I've not heard that.
And the relationship appeared to be after some kind of neotectonic.
Oh, there's a
activity.
lot of earthquakes in that area, yeah.
And so I think that kind of helps support what you're saying.
I wrote a proposal to the National Earthquake Hazard Reduction Program, and I felt like I was speaking the wrong language. These are all geophysicists out in California, and I'm not. Come on, this didn't make any sense to them, so it didn't. But I think we're going to go back. I'm going to go back with a geotechnical person. We're going to see what kind of shaking is required to generate something like that. Yes.
Sorry, I didn't quite catch how your conclusions differ from Laura Brown's
Okay.
conclusions. What was
The primary difference was she did not accept, and there's not a really good basis for it. She did not accept that there would be a buried lake deposit. We were never able to core deep enough to find out. We hundreds of cores from that area, but never could get through all that mud. So we didn't really get down. I predicted we would find lake material at the base. So we didn't do that. Where we cored in the pockmarks, we were just into glacial marine mud. And there's no gas beneath that. I mean, pockmarks have no gas beneath them, so it's clear that the gas is gone. I inferred this just based on the regional geology, what I'd seen in other places. She inferred that it was just the Penobscot River's there, a large muddy river, that it was muddy river mud coming out, bringing organic matter that got buried, and it was just the natural evolution of the bay that's going to come out. It doesn't explain to me why the Susquehanna River hasn't delivered such organic matter to Chesapeake Bay, and why it isn't just covered with pockmarks. It isn't. There aren't any. So I looked for something unique to Maine about burying really rich bodies of organic matter, lakes for the most part, and wetlands. Because of our uneven glaciated terrain, we have those things, and that's my feeling for why we have pockmarks and you don't find them in the coastal plain. But I could be wrong.
Okay, thank you.
I didn't tell you all of that. I was wrong on a lot of things in here, but we didn't go into that. So if you got some great equipment you want to bring up to Maine, we've still got untouched bays. Nobody's even turned a piece of equipment on in the bays. It's a great place.
Ben, we did one survey up there, didn't we? Ben?
Yeah.
Whereabouts?
Castine, Bagadoo.
Oh, you went up there? Oh, you're up in the Bagadoos. I've never gone in there.
It was an exciting survey, where the current was running.
Oh, they have a tidal. They have a tidal energy facility
Yes.
there now.
Yeah, that's why we.
Were you there for that? Okay.
Well, we were doing it for our field camp. And so we have to do, every year our students go up and
That's
survey
why.
someplace.
That's why John came down. He wanted to find someplace new for them to go.
And your places are a little far, but we could do that some year.
Oh.
Ben's the captain of the vessel.
I can suggest some great areas to do that are really interesting.
He has to get in line.
Yeah, probably true. So I envy you. You got a great program and a great situation here. This is really good.
All right, well, thank you.
Okay.
again.
Thank you.